Great, thanks for coming. I just want to start with a quick survey. How many of you have beliefs? You believe anything at all? Good. And then how many of you, when you get some data that maybe isn't consistent with your belief, you update your belief? Oh, should be more of you, but okay, good. Looks like we got some internet trolls that didn't raise their hand. Cool, so yeah, it's basically what Bayesian statistics is, and that's what we'll be talking about today. So first I'll motivate a little bit about why we want to use Bayesian experimentation. There are some challenges with it, and these are reasons that people have avoided using Bayesian experimentation and have mostly used frequentist experimentation. So we'll talk about those. One is where do we get priors, and then whether or not it's going to be fast enough, and generally if we can find a generally applicable solution to generating Bayesian posteriors. I'm going to breeze through this pretty quick because the meat of it is really a statistical method we use called bootstrapping and how we can do that efficiently. So Paul will be talking about that. And then, you know, as you all know, these talks are very short, so Q&A will probably be like in the halls or over lunch. We probably won't have time in this room. Cool, so why Bayesian experimentation? There's a bunch of reasons. I've only listed 3 here. One is that Bayesian statistics give you a little bit more natural interpretations of the data. It's a little bit harder for laypersons to understand some of the interpretations of frequentist statistics. It also gives you sequential updating automatically. I mean, that's just a natural feature of Bayesian statistics. Whereas if you do something, so in frequentist experimentation, there's often a problem of peaking, where if you look at the data too much, you have to apply corrections to it. Well, you get that sort of for free with Bayesian experimentation. And it's also well suited for optimization problems. So you'll see this Bayesian posteriors used a lot in multi-armed bandits for sampling different arms in multi-armed bandits. Nonetheless, there are some challenges. One is how do you come up with priors? So in order to get a posterior, you need priors. And for a long time, Bayesians used non-informative priors, which was sort of a cop-out. But more and more, you see people thinking that you really need motivated priors to use Bayesian experimentation or Bayesian statistics to its fullest. So additionally, like let's say you do have priors for a particular metric. Coming up with priors for all these different metrics can be a lot of work because they're all parameterized differently. And then even if you come up with priors, you might wonder like, well, can we efficiently compute the posteriors for all these metrics? So these are some of the challenges we set out to solve. The first one is where do we get priors? And just to make sure everybody's on the same page, because I know not everybody's Bayesian, I'm going to talk a little bit about what priors are. So I'm going to start with this guy, Peter Griffin, who has this belief. So priors are just prior beliefs, stuff you believe before you have data. So, you know, Peter might think, well, there's something like a 30 to 50% chance that it'll rain tomorrow. So that's his prior belief. And then he gets some data. So the weather forecaster says, look, there's an 80% chance it'll rain tomorrow. So now you have the prior and you have this data. Well, you should update your belief. You should say, OK, well, given that, depending on how strong your prior was, you say something like, there's a 60 to 80% chance that it'll rain tomorrow. So that's the general process. Representing it as distributions, again, on the left is the prior. So it might be centered around like 0.4. You get some data, and then depending on how strong your prior is, you update your posterior, which is a mix of the prior and the data. The data is the easy part. We all have data, so today we'll be talking about how to get priors and posteriors. This is just an obligatory slide that shows Bayes' theorem. Every Bayesian talk has to include this theorem. It's a Bayesian law. So that's what priors are. How do you come up with priors for experimentation? I'll talk a little bit about why it's challenging. So imagine that you just have one metric and it's revenue and it's distributed like this. So you have a lot of people who don't convert. So revenue for those people is 0. And then you have some distribution. The rest of the distribution is like actual revenue from people. So you might wonder like, well, how do I model that? So maybe you can come up with some probabilistic function that says, you know, there's some probability p that people will convert or not. That's the Bernoulli trial. And then if they don't convert, obviously revenue is 0. That's easy. If they do convert, revenue is a random distribution from a gamma distribution with some parameters, let's say alpha and beta. So you have these parameters from which the data is generated, from which you're sampling from the population. And you need to come up with priors. So the first thing you need is a prior on p. So what is the chance that somebody actually converts? And that prior is going to be represented as a distribution because you don't know exactly what that p will be, but you think it will be within a certain range. So you express that as a distribution. And then the tilde here is just, it means that we're getting a random draw from that distribution. And then we also need a prior for the gamma portion of the distribution, so for the alpha and beta parameters. And those alpha and beta parameters will be distributed from some prior that we have. So that's our prior. So that's pretty straightforward. We can do that pretty straightforwardly. But now we need to do it for all these different metrics that our project manager says they care about, right? So every project manager will say, hey, I want a metrics dashboard with tens of thousands of metrics because they're all important. So the problem is that these different metrics have different distributions, and those different distributions have different parameters. So then you have to come up with priors that all have these different types of parameters, and that's not straightforward. This is an actual video of a project manager asking me for more metrics on the dashboard. It doesn't go well. So there's a pretty straightforward solution to this. It's the same thing that you would use in null hypothesis significance testing. So in null hypothesis significance testing, so for example, t-test, what you do is you actually don't look at the parameters of the distribution. You look at the metric of interest. So if you're using a t-test, you're actually wondering, like, what is the distribution of my mean, my population mean, given this data? And then you ask for the variant. So you have this distribution of means that's distributed as a student t distribution. You have this distribution of means for the control. And then you want to know, well, is my variance different? That's sort of statistical significance. Is it statistically different? So you're asking, is that variant mean within the 95% confidence interval of that student t distribution? So it looks sort of like this. If your variant mean falls within there, then it's not statistically significant. If it falls outside of there, it is statistically significant. So that's the problem. Or that's the way that the frequentist approaches it. And it works fairly well for all types of distributions. You might hear that there's an assumption that for a t-test, the underlying distribution is normal, but actually it's pretty robust for all types of distributions with large enough sample size. So it turns out you could actually do the same thing with Bayesian priors. So with Bayesian priors, you can actually look at the metric of interest, the means, for example. You know that that's going to be normally distributed because of the central limit theorem. So the nice thing about that is, before when we were saying, well, look, all of these different distributions have all these different parameters, a normal distribution always has the same parameters regardless of the underlying distribution. So whatever the distribution is on the left, whether we care about revenue or clicks, it doesn't matter how that's distributed. The means of that are going to be distributed normally. So the nice thing about that is the parameters will always be just the mean and the standard deviation of that distribution. And so your priors can always be represented as a normal distribution and, say, inverse gamma for the standard deviation. Moreover, there's some interesting data. So Ronnie K has a paper where he talks about a meta-analysis of experiments across a bunch of different companies like Microsoft and Netflix. And it turns out that most experiments actually don't have any effect at all. So this is a good way for you to form a prior belief about what a new experiment, what effect it will have. And your prior belief really should be that most experiments aren't going to have any effect at all. So what that means is that if you look at that normal distribution in the top right, the mean of that can always just be set to whatever the mean of the control is. So that should be your prior belief, that there's actually no difference between the control and the variant. And then you can get the parameters for your inverse gamma distribution just from historical data. That's really just the variance of the sampling mean, the sampling distribution of the means. So that's the solution to where do you get your priors. The nice thing is it's generalizable and scalable, and you don't have to worry about handling it for a bunch of different metrics. And so another question that people have is Bayesian experimentation fast enough and generally applicable? And one of the reasons they ask this is that there's a way to compute priors for distributions called Markov chain Monte Carlo processes. If you're interested in that, I saw that Avi from Stripe is going to be doing a talk at 110. I'll be there. It sounds really interesting. But the problem is that that process is actually computationally quite expensive and fairly slow. So we've answered the question, like, how do you come up with priors? And now the question is, can we efficiently compute the posteriors for all these metrics? The nice thing about using a distribution of means is that we don't have to compute the posterior with MCMC because that's fairly expensive, because it has something called a conjugate prior. So a normal distribution has something called a conjugate prior, which has a closed form solution to computing the posterior. So the nice thing about that is that our data is normally distributed, so our prior, to get from our prior plus our data to our posterior, it's actually really fast. So we don't have to do some random sampling like you do in Markov chain Monte Carlo simulations. We can actually just run it through our closed form solution and get a really fast answer to what our posterior distribution is. So one other thing that I'm going to mention is why are we using bootstrapping. So for the data, there are a few reasons that you might want to use bootstrapping to get your distribution of means for your data. So there's different papers on why this is the case, but some of them are related to like model misspecification or non-independence of bandit arms. So we want to use, for our experimentation system, we use it both for like traditional A/B experiments as well as bandit type experiments. And we want to make sure that our approach is generalizable. So bootstrapping is an important way for us to get good estimates of our sampling distributions. But bootstrapping is a little bit expensive. So it's not as expensive as MCMC. It's a little bit expensive. So we've done a lot of work on trying to make that more efficient so that we can make our experimentation pipeline run faster, fast enough so that our product managers don't come ask us when the experimentation pipeline is going to finish running. So that's what Paul's going to talk about.
All right. So I'm going to talk about what bootstrapping is and some of the ways that we've tried to overcome its computational cost. So to illustrate bootstrapping, let's say that we had some sample data for an experiment. So each letter here is supposed to represent a revenue value for a given visitor in our experiment. So to generate a bootstrap sample, we'll sample from this data set with replacement 7 times, so the same number of times as the size of our original data. And we're doing this with replacement. So once we have that sample, we compute whatever statistic that we're interested in. So in this case, we might look for the mean of our revenue. And then you repeat this process a large amount of times. So you want to repeat this procedure as many times as required to have a sufficiently precise estimate of your sampling distribution. So this result here is a collection of values that represent your sampling distribution. And you can generate some properties of that distribution for your analysis. So here's that same procedure, just in words. So as you can tell, it's a very computationally expensive procedure, generating thousands of bootstrap samples. It takes a long time. And when we're talking about the scale of online experimentation, the data sets are so large that they don't fit in memory usually. So this is kind of like a classic big data problem. So we set out to tackle it using Spark. And Spark is, as you know, it's useful for handling large amounts of data and processing it in parallel across multiple machines. But as we were approaching this problem of implementing bootstrapping using Spark, we quickly realized an issue with the way that Spark is typically used. So just to illustrate, let's say that we had our data in this RDD. Usually what happens is you partition your data, and tasks on those partitions are distributed among your workers. So we thought, okay, how can we generate a bootstrap sample in a way that's distributed using Spark? A natural way to think that you could do this is by saying, why don't we just generate a fraction of the samples required from each partition? So say we have 7 partitions. We can generate n over 7 samples, where n is the total size of your original data set. You do this for all your partitions. And if you combine them, you have a full bootstrap sample. So this doesn't work, and the reason why it doesn't is because this doesn't actually count as bootstrapping. So remember that when we're bootstrapping, we have to sample with replacement. So each draw should be completely independent. So a way to check to see whether it's a valid Bootstrap sample or not is to see if the procedure is such that it's possible to generate a sample where every sample is the same value. So that should be possible if we're actually sampling with replacement, but it isn't here. So we kind of considered other ways to distribute this work, but there were issues with those as well. So we thought of, okay, what if we can compress our data set so that each worker in our cluster can generate the Bootstrap samples independently and in parallel. So we could use the feature of Spark broadcasting where we could take our compressed data set, broadcast it to all our nodes, and so that the data set is available for all our workers to generate the Bootstrap samples in parallel. So as we were thinking about how can we compress our data set so that it fits in memory, as well as so that we can sample from it in a way that has the right properties, we realized that our experiment data has a very low cardinality compared to, so it has the number of unique revenue values is quite small compared to the size of the original data set. So that's typical for an online marketplace like Udemy. And most of them are actually zero because conversion rates are typically low in online marketplaces. So what we decided to do was, the idea that we had was to compress the data by constructing a frequency distribution and sampling from that distribution. So to illustrate, we have some example fake data here where on the left we have some visitor identifier, and then on the right is the metric value for that visitor in a particular variant of an experiment. So what we do here, from that we construct a frequency distribution. So here on the left are all the unique values that occur in our data set, and on the right are the counts of each of those unique values. So just one thing to note that this collection is sorted by frequency in descending order. That'll become important later as we talk about how we sample from this. But at this point, we were able to compress our data small enough to fit in memory for all our experiments. So now, how do we sample from this data? So to do that, we then construct a collection of cumulative frequencies. So each entry in this collection, the cumulative frequency is the sum of the previous cumulative frequency plus the current frequency. So yeah, and so the last entry of this collection should be the least frequent number because we've sorted by frequency, and then the cumulative frequency of that final row should be n, the size of the original data set. So now these cumulative frequencies can represent the upper bound of the range of indices that represent the value on the left. So now to sample from this, this collection, we just sample we draw a random index from 0 to n minus 1, and then we retrieve the value by checking which range the index falls into, and then we take that value out. So some things to say about this approach. So the way that we chose to do this was by starting from the top and checking to see if it falls under that range, and if not, go on to the next one until you get to the right range of indices, and then retrieve your value that way. So in the worst case, if we randomly sample an index n, we have to, or n minus 1 I should say, we have to traverse the entire collection to retrieve that value. But actually most of the time, and this is why the sorting by frequencies is important, because most of the time we're actually spending around the top of the collection. And if you were to construct or plot the distribution, the time complexity is the expectation of this distribution of your unique values. So there are some assumptions about the sparsity and distribution of your data for this approach to work. And there's other optimizations you can make. So if that tail is like really, really long, you can use a binary search tree instead. But yeah, so this is what we have in production in our analysis pipeline today. and it's working fine for daily batch processing. Yeah. So the other thing that I wanted to talk about is just kind of like an idea that we have for doing this faster. So currently, we're sort of limited to daily batch processing. And what we do, a challenge that we have with bootstrapping is that every time the data is updated, say a new visitor is added to the experiment, or the metric for a particular visitor changes, we have to kind of scrap all the work that we did before and start from scratch with the bootstrapping to estimate the sampling distribution. So we kind of thought about, is there a way that we can update our bootstraps? So to illustrate this idea, let's say we had an experiment that just started and 6 visitors were added to the experiment. So to generate a single bootstrap sample, again, we sample with replacement 6 times. So let's say we did that. And then 3 new visitors were added to the experiment minutes later, let's say. So what we do today, we kind of scrap all the work we did before and then start over. We sample 9 times with replacement from this full data set. But is there a way that we can update the previously bootstrapped sample to reflect the addition of our new visitors? So we can ask, okay, if I went back in time, what is the probability at each step of the sequence of random samples that I would have drawn from one of our new visitors? So that probability is 3 out of 9, right? So what we can do is we can conduct a Bernoulli trial at each slot in the sequence to see whether or not we would have actually chosen a new visitor. So we could do that, and let's say that the only success was at the 2nd slot. And we replace that with a random draw from our new set of visitors. And then for the remaining 3 slots, we just draw from the full data set, from all 9 visitors. So this is a way that you might be able to update Bootstraps to reflect new data. And actually, we don't have to conduct all these, a Bernoulli trial for each slot of this sequence, because the distribution of n independent Bernoulli trials has a known distribution called the binomial distribution. So actually, we just have to draw once from the binomial distribution, where n is 6, the size of the original data, and then p is 3 over 9. So the size of the set of new visitors divided by the full data set. So this is kind of just a way that we thought that we can, an approach that we can go with to be able to update our analyses faster by updating our bootstraps. There's a lot of work that still needs to be done. Obviously, this is all we have, basically. There's a lot of open questions that we have, namely, how do we efficiently store and persist our bootstrap data, which is something that we're not doing today. But yeah, that's something that we're working on, and we'd love to hear ideas that you might have. Yeah, I'm gonna hand it back to Robert to wrap up.
Okay, cool. Just to recap, so we covered why Bayesian experimentation, some of the challenges, like where do we get priors, and is it fast enough and generally applicable? And then can we make it faster? Like Paul said, we're working on some techniques for being able to do more like real-time processing or experimentation data, which you can't really do if you're bootstrapping full data sets. So we have some resources. We've just started open sourcing our statistics libraries. They're written in Scala. They're very early stages, so if you're interested in contributing, that would be great. The technique that Paul mentioned with cumulative frequencies, we have that in our Spark statistics library. So you could start using that today. And then we plan to roll out more bootstrapping algorithms, like the more real-time bootstrapping algorithms as we develop them. Also, if you're interested in working on these sorts of things, Udemy is hiring, so go to that link if you're interested in that. And then feel free to grab us in the hall. Oh, also on our data and engineering blog, we have a couple posts about bootstrapping. So Paul goes more into depth about stuff he was talking about today. So feel free to visit that as well. And then grab us in the hall or at lunch if you have questions.